like last Tuesday, I think, no, maybe it was last Monday, we talked about the difference between solving an equation and evaluating an expression, right? When you evaluate an expression, you're given a value for the variable and you plug it in to get a value for the expression. And when you solve an equation, you're given a value for the expression and you plug that in and then solve for the variable. So we have sort of analogous ideas when it comes to function notation, right? They can give you the input of the function or they can give you the output of the function. So if f of x is, I don't know what I called this, like, I'll just make something up. Let's go with 9x minus 4. If I say evaluate f of 5, this is just like when we were evaluating expressions, right? I give you an expression, I give you a value for x, you plug that value in and you get the value of the expression. So this is when we're given the input and we find the output. The best way to identify if you're given the input or the output is to look in the parentheses next to the f. If there's a number there, you are given the input. If there is not a number there, you are not given the input. So in this case, there's a number, right? It's f of 5, and so our input is 5. We did this yesterday, but we'll do it one more time. 9 times 5 minus 4 gives me like 30, no?
41.
Thank you. 41. So we are given the input 5, we found the output 41. The other type of problem is more like what we do when we're solving an equation. So if we're, and it's usually worded that way too, it says something like solve f of x equals 32. In this case, again, if you look in the parentheses next to the f, there's a variable there, which means you don't know what the input is. So what's in those parentheses is always your input. If there's not a number, then you can't plug a number in for x. So in this case, remember that this whole symbol represents the output. And so if they tell us that f of x is equal to 32, they're saying the output of the function evaluated for some x is 32. We don't know what that x is in this case, and so that's our job, is to find the x. So in this case, we are given the output, and we want to find the input. And we do that just by replacing the f of x in our function notation with the number they give us. So that entire thing, f of x, not just the x, but the whole entire left side, we're going to replace with 32. So we have 32 equals 9x minus 4. And then we just have a regular old equation that we know how to solve. So we add 4 to both sides. And we divide by 9, so we get 4 equals x. And so those are sort of the two types of things we can get is anytime they say f of x equals a number, they're giving you the output. Anytime they say find f of some specific number, they're giving you the input. So like I said, probably the simplest way to figure out which one it is to look in these parentheses. And if there's a number there, you know what your input is. If there's not a number, you don't know what your input is, which means they must have given you the output or else you can't really find anything. So I know there was like one like that on your homework last night, like solve c of x equals like 41 or whatever. If you didn't get it, that's totally fine. That's what corrections are for now that we've talked about it a little bit more. Does that make sense, how to tell the difference between those two situations? Any questions? Okay, so I also want to talk a little bit about evaluating when our inputs aren't just numbers, so when they're variables or even expressions. I don't want that yet. So if I have f of x equals 2x plus 9. And I want to evaluate, let's call this part A. F of, I don't know, what's your favorite letter? Z. Be careful with Z's. I always put a hash mark through it because they really can look like 2's. There's all these little tricks like T's. If you put a little curly guy on the end, it won't look like a plus sign. We don't use L's all that often because they sure look like 1's, and nobody ever uses O's, right? That's all sorts of confusing. So if I want to evaluate f of z, are they giving me an input or are they giving me an output? Yeah, they're giving me an input. So this is tricky because we just said if there's not a number there, they're not giving you the input, right? But remember that z represents a number. So as long as what's in there is different than what's in the parentheses in the original statement, then they've given you something new to input into the function. So here they're saying evaluate our function for an input of z. Remember, our function is just a set of operations. It says take your input, multiply it by 2, add 9 to it. And so if my input is z, I'm going to multiply z by 2 and add 9 to it. Not super duper exciting because we don't get to do anything or find a numerical value, but that's all that means. You can think of this as f of something equals 2 times something plus 9. So if they give you this, you just put the same thing in this spot every single time. So if you have f of anything, then the right side is going to look like 2 times that thing plus 9. So next we're going to evaluate f of z plus h. So remember, what's in the parentheses is your input. So what am I actually inputting into f in this case? I'll give you two choices. It's either z or z plus h. Yeah, it's just z. So this one can be a little bit tricky because that plus h, you feel like you should do something with it. But what this is really saying is input z into f because the only thing in the parentheses is that z. And then whatever output you get, which is represented by that f of z, you're just going to add h to that. So we're just going to tag on a plus h after we evaluate. So f of z is the same as what it was in the previous problem. So f of z plus h equals 2z plus 9. So this is my f of z. And then it's just saying once you figure out what f of z is, tag a plus h onto the end. So one thing we talk about a lot, especially once we start doing transformations and things like that, is if we're acting on the input of a function or if we're acting on the output of a function. So you can do addition, subtraction, multiplication to an input before you apply your function, or you can apply your function and then do addition, multiplication, subtraction, addition to whatever you get as the output. In this case, we're performing the operation plus h on the output of the function because it's outside of those parentheses. So if we're acting on the input, it would be inside. Yes?
So wouldn't it be a minus h, 2z plus 9 minus h?
So you're thinking of solving, but we the left side and the right side, we literally want to be exactly the same. So whoops, wrong one. F of z is 2z plus 9. And so f of z plus h is that plus h. So we're not actually trying to get anything alone. So we only do opposite operations if we don't want that h on the right side, in which case we would then subtract it. But for our purposes here, we want the left and right side to represent exactly the same thing. So they should perform the same operations. All we did was say f of z is performing the operation times 2 plus 9 on z, and so we replace that piece of it. So in contrast, we could do the same operation of adding h, but act on the input of the function. So that would look like f of z plus h. So now inside the parentheses, we're adding h, which means we're adding h to our input first, and then we are acting on that using f. So the operations multiply by 2 and add 9, we want to apply to z plus h as a whole, rather than adding h after applying those operations. So just like we have up there, whatever's in those parentheses, I'm going to multiply by 2, and then add 9.
Do you have to add another h on the end?
Nope, because it's just part of the input in this case. So, and we can distribute, like, it's not super exciting. But we can kind of think of, like, if we think of the machine type idea that we talked about yesterday with, like, the picture. If I start with an input of z, and I put it into f, then I get f of z out, right? And so if I want to add h after that, I'm adding h to the input, and that gets me f of z plus h, as opposed to starting with z plus h, putting that into my function, and that's going to give me f of z plus h. So I don't want to do any operations after I've applied f, because there's no operations outside that f of whatever. So you can kind of see, like, the difference between, like, acting on the input and acting on the output based on where you're adding that h. Like, if you add it after putting your input into the machine, or if you do it before you put the input into the machine. So it's one of those things that, like, in writing, parentheses don't make a huge difference, right? If you drop parentheses and just had an extra sentence, it would sort of still mean the same thing. In math, parentheses are one of the most important things that can change the meaning of an expression, like where they're placed and whether or not you have them. Like, completely changes the meaning of the expression, because it has to do with order of operations. It's like, am I adding h first and then doing all of this, or am I doing all of this and then adding h? And that's what the parentheses always tell us, is do this first as opposed to do it in just straight order of operations. So, like I said yesterday, you guys will get so many opportunities to practice all of this. So if you're not 100% comfortable with it yet, that's okay. We will do it for 15 weeks. 13 and a half now. Okay, so the next thing I want to talk about before we get into domains and ranges is just graphing functions. And we're not going to do a ton, because once you sort of see the relationship, where the heck did it go? Oh, there it is. Once you see the relationship between, like, x, y type equations and function notation, we sort of see that it's not anything really all that different than just graphing y equals x plus 5 or whatever your equation happens to be. So we have this definition. So the statement y equals f of x, or I guess I usually write it the other way, f of x equals y, means that the y coordinate of any point on the graph of f is obtained by evaluating f for I should say with the x coordinate as the input. So this statement is something you'll see quite often. It's just our way of relating our function notation, which doesn't have a y in it, to the xy coordinate plane where the vertical axis represents y coordinates. This is a lot of words and it kind of looks like it should mean something important, but really it just means that these things behave the way you want them to, that graphing f of x equals x plus 5 is the same as graphing the line y equals x plus 5. So if I plug the x value of 2 into f of x equals x plus 5, I get 7. That means that the point 2, 7 is on the graph of the function. So the statement f of x plus y, f of x equals y is the same as saying the point xy is on the graph. Of f. So it's mostly a language and notation thing. So to graph functions, we are going to focus exclusively on just making a little table, plotting some points, and drawing a curve through them. As we get more into different types of functions and how they behave, we'll talk more about some other ways you can graph functions by using a general shape and transforming it by shifting or stretching or flipping. But one thing to keep in mind is that if you have no idea how to graph something, you can always just pick a bunch of x values, plug them into the equation, get a bunch of y values, and draw a bunch of dots, and then connect them. So it's always something you can fall back on, even if you completely blank on the other ways that you can graph that we'll talk about later in the semester. Just plotting a bunch of points is a method you can always fall back on to graph a function. So let's graph f of x equals 2x squared plus 9. Whoops, minus 9. Remember that when we were talking about solving equations, we said linear equations. You could identify because there's no exponent on the variable. So the same is true with functions. Linear functions have no exponent on your variable, and those are the only ones that'll get you a straight line, which means for any function that's not linear, you need more than 2 points, because the only thing 2 points will give you is a straight line, right? We won't be able to see how something curves just by looking at 2 points. So I usually recommend, until you get super familiar with the different shapes functions have based on the type of function it is, that you do like at least 5 points. And that should always include some negatives, some positives, and 0, because a lot of functions change their behavior at 0. So we want to make sure that we have a good enough points to get a good idea of what the whole thing looks like. So we have a table here. We've got x values, and then remember our y values we get just by plugging our x values into the rule. So I'm a little bit boring. I kind of always use the same 5 numbers. You don't have to use the same 5 numbers I use, again, as long as you pick a few negatives, a few positives, and 0. I wouldn't recommend using something huge like 5 billion because you're going to have a hard time finding that on your graph. And then definitely use a calculator for these calculations. I know if you took 065 last semester, you've gotten super used to not reaching for your calculator, but it's going to save you a ton of time on things like this where you have to do simple calculations repeatedly. So we have 2 times negative 2 squared minus 9, and that's negative 1. 2 times negative 1 squared minus 9 is negative 7. 2 times 0 squared minus 9 is negative 9. 2 times 1 squared minus 9 is negative, 7. And 2 times 2 squared minus 9 is negative 1. So each line gives us a point on our graph. If x is negative 2, y is negative 1. So when I ask you to graph on like tests or even on homework, I'll always give you like a grid. So you don't have to worry about like labeling these guys as far as labeling the axes or anything. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's negative 10.
Sorry.
Is everybody familiar with plotting ordered pairs? Like how to find where that is on a graph? If it's at all confusing to you or you feel rusty on it, feel free to come by. We can go over that in more detail. But so if x is negative 2, y is negative 1, that's negative 2, negative 1, that's a point right here. If x is negative 1, y is negative 7, 9, 8, 7, which is right here. When x is 0, y is negative 9. When x is 1, y is negative 7. And when x is 2, y is negative 1. So that gives me those 5 points. And you can kind of see already, like this, there's nothing really linear about this, right? Because it doesn't, like, the points aren't separated by, like, the same distance, right? It gets steeper as it goes. So one thing to keep in mind is that the only functions that have straight lines are linear functions. The one exception is the absolute value function, which is made up of 2 linear functions, like straight line. But all other functions that we'll deal with are curves. And in particular, they're what we call smooth curves, which means that they don't have any straight lines and they don't have any sharp corners. So for this one, for instance, that bottom bit where we turn around is a U, not a V. And smoothness is an important concept as far as when you get to calculus and taking derivatives, because you can't take the derivative at a corner. You can only take the derivative of smooth functions. So we say you want to draw a smooth curve through the points once you get them. So I'm a horrible artist, so I'm certainly not going to judge you on your ability to draw like a perfect graph, but it should look like you know what it should look like, basically. If I see like really straight lines, then I'll think that you probably think that there's straight lines in it. So this is going to come through here and up through this guy. I don't really like what I did there. So it's going to look something like that. Any questions about how we got there? Is that pretty clear once we know the notation and everything, how we're getting that table? Okay. There's one more I want to look at before we start talking about domains and ranges, which is the function f of x equals 3. So if I make a table here, what this is saying is that my output is 3, right? So remember that the right side of that function notation is the rule that tells you how to get your output if you know your input. If there is no variable over there, if there's no x on the right side, it just means that your output's the same no matter what your input is. So if I make a table here, if x is negative 2, what's y?
3.
Mm-hmm. What if x is negative 1?
3.
And then we start getting kind of redundant, right? But because there is no x on the right side, There's no operations that I can do with my specific input to get my output. I have to just be like, oh, the output is 3. So that's what f of x equals 3 means. It means regardless of what your x value is, your output is 3. What does this look like on a graph? Anybody know? Yeah, it's going to be a horizontal line because, remember, the y value gives you the height of your point, and so this is saying that all the points have the same height, and so it's just going to be a flat horizontal line. And if you know that it's a horizontal line, like, you don't have to make this table by any means. I just wanted you to see that constant. So this is what we call a constant function. Because the output is constant regardless of how we change the input. When we're graphing functions, we'll never see a vertical line. Anybody know why?
Because the x will always be different, or always be given.
So here, let me draw one. You're right, it has something to do with the x values. What can you say about the x values of all the points on that line? They're all the same. So that's saying that an input of 2 corresponds to an infinite number of outputs, right? Which makes it not a function. Like, it's a perfectly good line, but it's not a function because, remember, a function takes a single input and only goes to one output. Here, it doesn't pass the vertical line test, right? Because if we draw a vertical line on that red line, there's an infinite number of points on that red line that correspond to the same vertical line, so correspond to the same input. So there's nothing wrong with vertical lines, but they just don't happen to be functions. So when we're graphing a function, we're never going to end up with a vertical line. Okay, so I want to move on to domains and ranges. Let's do this first. So the first thing we want to talk about is just how we express sets. So we talked a bit about it last week when we were doing inequalities. We learned what interval notation looked like. So we want to just expand that a little bit so we can do a little bit more complex sets than just like all the numbers below something and all the numbers above something. So I'm going to draw a bunch of number lines. See if you can write in interval notation or some other set notation what set is represented by the shaded part of the number line. So let's see. Start with that one. And these are all separate sets. You're going to do a different set for each individual number line. So if you're not sure, just see if you can guess. It's okay if it's not right. I just mainly want you to think about it. Okay, so that first set, if we were to describe that in words, what would we say is in that set? So all the numbers that are what? Yeah, so all the numbers that are between 3 and -2, or -2 and 3, right? And graphing it like this really lends itself nicely to interval notation, because if these guys are labeled, like interval notation is literally like that, right? It's the smallest number in this set is -2, which we are not including. And then the largest number in the set is 3, which we are including. And inherent in this interval notation is the fact that everything in between is included. So all decimals, all fractions, every single possible number that is between -2 and 3 is included in that set. As opposed to this one, where the numbers in between, like -2 and -1 and 0, aren't included in the set, right? This is just individual points. And so we've seen that before when we first started talking about functions, right, where we just had a list of ordered pairs. So there were specific points, but all the in-betweens weren't included. And we use this like curly bracket to represent that and just listed. So in this case, -1, 0, 1, 2, 3. So these two sets are somewhat similar in that things in between -2 and 3, not including -2 and including 3, are in the set. But the difference is that in this second one, it's just those 5 integers. It's not all the numbers in between -2 and 3. So this is what we call a discrete set. And this is what we call continuous or interval. So the best way to identify if you're dealing with a discrete set or a continuous set is if you can see like individual dots, it's always discrete. Whereas when it's continuous, there's some sort of like curve or line that's connecting all the points. So just like on the, like we have here on our picture, right? We've connected everything between -2 and 3 in that first one, whereas in that second one, we just have individual points. What about that third one? What numbers are in that set and or not in the set? Mm-hmm. Yeah, this is really like two sets put together. It's everything less than 1, but not including 1. And then also everything greater than 1, but not including 1. So we can think of it as, so like Zachary said, we have -infinity up to 1, but we don't want to include 1. And then we want to start up again. Oh, sorry, I haven't talked about that yet. We want to start up again at 1, and there's no largest number in the set. So this is every single real number except for 1. So this is kind of the only way we can exclude just a single number, is to think of it as two separate sets, right? If this wasn't there, that would be the set -infinity to 1. And if this wasn't there, that would be the set 1 to infinity. If we put a hard bracket on either of these, then all of a sudden it's the whole number line. We haven't excluded anything, so there's no point in us having two separate intervals. So this is all real numbers. Except for 1. And to put these together into a single set, whenever we have two sets that we want to describe, like to use to describe a single set, because the domain of a function is the set of all inputs, we want both of those to be part of the set of all inputs. We use what's called a union symbol, which just means union. And that just means that the set in question is everything in one of those plus everything in the other one. So now let's see how we can use these notations to describe the domain and range of functions. We're going to start with using graphs to find the domain and range. This is just so you don't have to try to draw the graph. Okay, so remember that, I'll put it on this page. Remember that the domain of a function is the set of all inputs. Which on a graph is all of the x values that correspond to a point on your graph. So x values. And the range is the set of all outputs. And again, on a graph, that's just all your y values. So this first one is a discrete graph because we have individual points, right? None of them are connected by a line or a curve. Because it's a discrete graph, both our domain and our range are going to be discrete sets where we're just listing all of the x values and listing all of the y values. Oh, no. So, I thought you were making like a paper airplane to throw at me. So this is identical to what we did the other day where we just had like a list of ordered pairs. The only difference here is that we've plotted the ordered pairs on a graph as opposed to like listing them as ordered pairs. So my domain is just all of the x values. Again, it's discrete, so we're going to use the curly brackets. And then let's see, starting on the left, I have an x value of -3, an x value of -2, -1, 0, 1, 2, and 3. And again, remember, we can't say that's everything from -3 to 3 because we're not including the in-betweens, the decimals and the fractions. And then what about the range? So the range is all my y values. What y values are accounted for by points on this graph?
4, 2, 0.
Mm-hmm.
-2, -4, -2, 0.
Yeah, good. And there are 2 points that have a y value of 0 and 2 points that have a y value of -2. But remember from the other day, we don't repeat those, right? So once something is in the range, it's in there. You can use it as many times as you want. It's the correspondence itself that tells us if it's used more than once. So in set notation, we never repeat any numbers. Once they're in there, and you can grab them as many times as you need them. Now with a continuous graph, we're going to use interval notation to describe our domain and range. And the key to this is to remember that you want to think of them separately. So you want to think of all the x values, so you're only looking left to right. And then you want to think of all the y values, so you're only looking up and down. So if we look at the x values accounted for by this curve to find our domain, well, there's an arrow on the left side, which means that there's no smallest x value. And then if we move to the right, we see that there is no part of the graph past that line, right? So my x values are going to go from -infinity to 3. And because that's an open point, that point isn't actually included in my graph. So the ordered pair 3, -3 isn't actually a point that's part of my relation. So we use an open point to show that we get infinitely close, but we don't actually have a point there. So we're going to use a soft bracket to show that. And we're only thinking left and right. So this is literally like if we were graphing this on the number line. That's our domain. Where it happens to be vertically doesn't matter because we're only talking about x values. So when I say the domain is negative infinity to 3, what that means is if you pick any number that's less than 3, you will be able to find a point on the graph that has that number as an x value. So like 1 is less than 3. So if I pick the number 1, which is right here, I'll be able to find some point on the graph that has an x value of 1. Doesn't matter what the y value is. If it's in the domain, it just means there's some point on the graph with that x value. And then we're going to do the same thing with the y value for the range. Keep in mind you want to go bottom to top, which is a little bit not intuitive because we read top to bottom. But remember, intervals are smallest number to largest number. And so the smallest numbers are on the bottom and largest numbers are on the top. So we're starting on the bottom. There's no points on my graph below that line right there. So the lowest value in my range is -3. And again, because this is an open point, we're not including that. And then there's an arrow pointing up, which means that my graph goes all the way up to infinity. And again, you just want to think vertically here. It's really easy to get distracted about like where it is on the graph, but we're just talking up and down here. So we're saying if you pick any number between -3 and infinity, so any number greater than -3, there's some point that has that number as a y value. So like if I pick 0, here's a point that has a y, that's not true. If I pick 0, here is a point that has a y value of 0. And in fact, in this case, there's multiple points with a y value of 0. So that's mainly what you're doing on your homework tonight, is just looking at graphs and identifying the domain and range. Again, remember to think of them separately. So think horizontally for one, vertically for the other, completely independent of one another. Any questions on that as I hand back your homework?